Okay, should we get started? So you've nearly made it to the end of the tutorial section of CIDER. Everybody is so hyper-focused on seismology that I heard some unnameless person this morning, get confused between a route map for the Tour de France and primordial LLSVPs. I've also heard people that they really want to go and get lunch and sit in the sun, and I heard one brave soul say they've been looking forward to talking about the core. So that's what we're doing for the next hour and 25 minutes. We're going to talk about the core. And as is traditional for these things, you need to start with a slightly naff cartoon. This is hijacked from XKCD. There is some science on here, so moon-sized iron sphere, well, the inner core is a bit smaller than the moon. The inner core is about the size of Pluto, if you want to scale yourself. They tell us that it's at 3 million psi, so that's not really science then. But if you look at the conversion at the bottom, you'll see that the number we're given is about 207 GPa. So for the core itself, we're looking at a range of between about 140 GPa and 330 GPa. This is high pressure. I've also been told that the core is volumetrically insignificant, and I would argue that it's actually a weighty thing for us to think about. We have heard a little about some of the exciting things that the core does already this week. We've had John talking about the sorts of core physics which will make geodynamos happen, the exciting flows in the outer core, the turbulent behavior that will give us a magnetic field. If we have time at the end, and I've seen how everybody else's lectures have gone, so I'm saying if, we may get to talk about how some of those flows might actually influence behavior in the core. So how did we start? Well, as is tradition in seismology, we start with a chap with an amazing moustache. This is Richard Oldham. He actually grew up about 10 miles from where I grew up. And he made a number of interesting geological and seismological discoveries. In particular, he's famous for his study from 110 years ago, where he shows that there is a core. He's plotting travel times of primary arrivals and secondary arrivals, and he's drawing some lines through them, and he says, whoa, something weird is going on here. Let's have a distinct core at the center of the Earth. So there are a couple of things to point out here. First of all, seismology, though we would like to claim it, is not the first way that a core was hypothesized. That had actually happened something like 15 years beforehand. The second thing is, of course, he actually made some horrible mistakes in this figure, and so he gets credit for finding the core, and stuff is fairly wrong in many ways. So his secondary waves travel through the core. If his secondary waves are shear waves, and the core is liquid, that's obviously a little problematic from what we've heard for the last couple of weeks. He also has a nice smooth curve for his first waves, his P waves. What he's actually done is he's got probably these are P waves here, and you see this jump? Probably these are core PKP or PKIKP waves. I'm going to go through the naming in a bit. These S waves over here, and these are probably SS waves over here that are staying in the mantle and just bouncing around a bit. So, oops, but we have a core, that's fine. We'll sort out the details later. And it's actually not that much later. So this is now 1913. This is a paper which is in German, which I therefore cannot read, from Gutenberg. Last CIDER, I actually got 2 of the German junior participants to translate it for me. So pro tip, find somebody who speaks a useful language outsider. So the core radius that we have it from 1913 is about 3,500 kilometers. So we'll see that we're doing a fantastically and slightly terrifyingly good job at this point. And in the paper, Gutenberg points out that we would expect to see some interesting phases, like shear waves which have to be converted to P waves if they're to travel through the core. They're going to be SKS phases. We've heard a little bit about those, especially in Maureen's talk. We may get back to those today. And it's not that much later that we have Jeffreys saying, there seems no reason to deny that the Earth's metallic core is truly fluid. So it's not the strongest of statements ever, but already we're growing a story that looks like what we see with modern seismology. So because Quentin was slightly rude and interrupted and stole the mic, I put his favorite quote on the screen. I'm slightly worried he might throw things, but I feel like I'm safe over here. But actually what I'd like to say is that, first of all, this is not a quote, in my mind, aimed at mineral physicists. We used to suck at doing deep earth science. I think there are a number of things that we can be really quite confident of now. And there are also a number of things where we're not quite sure we're moving. So here is a list of maybe things that the discerning reader, as opposed to the unwary reader of Birch's papers, might like to think about. So let's expand the font size here and talk about this. This is kind of a layout for where we're going today. So we're going to talk about how the inner core is anisotropic. Rudy already talked very briefly about that, and we're going to spend a while talking about inner core anisotropy. Because although we know that there is at least some anisotropy in the inner core, we're kind of confused beyond that. We know that the inner core is solid. Jeffreys in 1926 said there was no reason to deny that. But we still have some problems matching mineral physics shear velocities with seismic shear velocities, and it's also pretty tricky to see shear waves in the inner core. So we'll talk a bit about that. The inner core is more viscous than the outer core, but we actually basically have no idea how viscous the inner core is. And people might argue with that, but estimates range from 10 to the 11 to 10 to the 22. And when you're ranging over 11 orders of magnitude, that should mean you're not tremendously sure. And we know that secular cooling of the core provides some of our energy for the geodynamo. It also provides some of our energy for mantle convection. I would argue, therefore, plate tectonics. I would argue, therefore, that the core is the most useful bit of the planet. And if anybody is reviewing one of my NSF grants, please write that. Despite that, we have a lot of concern over what the thermal conductivity of the core is. We don't know that much about some of the behaviors and some of the budgets that we have there. So at the very end, if we get time, we shall talk about that. So, onwards through history. We've zoomed all the way forward to 1936, and we now have Inge Lehmann doing some tremendous observational seismology, finding some unexpected core arrivals, and suggesting that in the center of the Earth, we have some sort of solid body. Now, those with a keen eye will notice that these are straight lines that Lehmann drew through the Earth. But she still managed to estimate a core radius within a couple of 100 kilometers of the inner core of what we have today. So even with simple approximations, you can get a reasonable feel for what the core does. So what do we see seismically? Well, seismically, what your seismologist will want to do is go and grab a velocity model and predict you some ray paths and travel times. At least if they're me and you normally work with ray theory. If you want to do finite element, you might be there for a couple of weeks sorting that out. So here we have three of our favorite models for velocity. This is VP I'm plotting for the core. We see that there's reasonable agreement. We see a couple of places where there's some disagreement. Arguably, those are closest to the interesting boundaries. So this is the top of the outer core. We see a little bit of spread in those velocities. This scale, it's quite kind of hard to discern because the mantle is so super fast. We also see that there's some changes going on here around the inner core boundary. So these are the sorts of differences that we would have in our 1D velocity models. I would also say that there's a 4-kilometer difference between these two models of where the inner core boundary is. So some of these differences, I mean, it's not a big percentage of the inner core radius, but we do start to see differences even between sensible 1D models. Okay, so we have some models. So now the next thing we should want to do is go and talk to our mineral physics friends. What I'm plotting up here for you are some data taken just from one mineral physics paper that was summarizing a bunch of stuff. This is density plotted here on the x-axis in both figures. On the y-axis we have VP here and VS here. These shear wave velocities and these P wave velocities and these densities correspond to iron either with different alloying elements or in different crystal systems. So we have iron sulfide, iron silicate, we have body-centered cubic iron, we have hexagonal close-packed iron, and then the black dots correspond to PREM. So you see a bunch of scatter in these data. That's actually one of the reasons is because they're made at different temperatures. So for example, for the BCC iron, so what we're seeing here in green, the temperature range used for these calculations goes from 750 Kelvin to 6,000 Kelvin. So we're seeing scatter in the mineral physics. And I would point out that this is not the most recent data. When we look at this picture, we see that we can get PREM to sit in VP and density space near some of the points. it's actually near a couple of different points. We've got HCP and BCC iron. We can't have pure iron in the core because then it would be too heavy. The mass would be too high. But we can see we can get close. Things become a little bit more problematic when we try and match shear velocity. So for sensible temperature estimates, and assuming that everything is solid, it's kind of tricky to simultaneously match density and VP and VS for the core. So that's something to bear in mind. And this picture is just showing you the effects of sulfur and the effects of silicon. So what other light elements have people talked about for the core? This is one of those super cheeky figures that people make. I didn't make it. This was made by a mineral physicist. He's making fun of other mineral physicists. I therefore believe that this is okay and legitimate. What you're seeing here is year of publication versus number of articles for a range of different light elements that have been suggested. You'll see that sulfur and silicon and oxygen are really the major players if you go kind of volumetrically by publication. You'll see that carbon is on some sort of a charge, that hydrogen is just kind of hanging in there, but it doesn't look like it's about to win the race. I would leave this question completely open to the mineral physicists. You can all shout out your favorite mineral if you want, that's fine. What I would say is that probably you can't just do everything with one light alloying element. That's probably not okay. I show you one figure here from some work by James Badrow. He's doing what many people would try and do, and he's trying to match PREM. So here, this is for the outer core. He suggests that you really need some oxygen and then some combination of sulfur and silicon and carbon to match the properties that are roughly associated with PREM in the outer core. I would caution everybody who hasn't been to one of these meetings before to remember that PREM is not the Earth. PREM is a model which tries to represent some of the Earth. So although we think PREM is a good fit for basic Earth structure, we know that PREM and other models are not perfect. So please don't trust us seismologists completely. We're fairly good, but we're not magic. Okay, that's my mineral physics detour. So now all the mineral physicists in the room hate me. That's fabulous. Let's move on and see how many seismologists I can annoy. Let's start with the really simple stuff. We haven't had too much of the seismology alphabet soup in the past fortnight. So here is your chance to hear ridiculously labeled seismic phases and get confused. If I confuse you, please wave at me and I'll try and re-explain what the different phases are as we go through this morning. So we have an earthquake. Our earthquake is represented by a star because we pretend it's like a big bang somewhere. That's actually kind of true for some of the most useful data from nuclear tests that we look at for the inner core. We see a number of phases here. PKIKP is shown in red. That's going to travel through the mantle. It's going to travel through the outer core, through the inner core, and then back up to be detected at this strangely triangular seismic station. We also call PKIKP PKPDF. That's just a labeling convention. We see the purple line next to that, PK little IKP, and so you really do actually have to say little I in the middle of that. PK little IKP actually bounces off the inner core boundary. Okay? So it cares a lot about the properties at that interface. The chaps labeled here in blue and then in green are PKPBC and PKPAB. They're just seismic phases which make it into the outer core, never quite get to the inner core, and then come back up to the surface. And they're very often used as reference phases. The trick that seismologists will use here, and it's in some ways very similar to the splitting trick that Maureen talked about, is if you have phases which are similar in the bits of the Earth you don't care about, and here, and I apologize deeply, I barely even notice the crust. Like, there's hardly any crust in my world. I don't really care that much about the mantle when I'm thinking about the core, so if our paths are similar here, and they're generated by the same earthquake, and they're recorded at the same station, then we can look at relative differential travel time, so relative travel times between our inner core wave and one of our outer core reference waves. And we can say the outer core, pretty well mixed. So we can ascribe a lot of our signal to the inner core. There are always going to be complications due to mantle structure, and those are hard to avoid, but this trick will reduce some of them.
What's the difference between the AB and the BC branch? And it seems like those are violating Snell's law.
They're not super rebellious and violating Snell's law. What you actually have is an exciting shaped travel time curve. So this is travel time, and this is distance. And due to the shape of the velocity profile between the mantle and the outer core, what you actually get are these triplications. And so our BC and our AB are part of the triplicated phase there, due to that velocity profile. That has an interesting side effect, that you actually have a pi/2 phase shift as you go from the PKP BC, which has the same phase shape as your inner core phase, to the PKP AB. So if you want to make measurements between those two, you actually have to take into account the triplication and the change in phase shape that you'll see in the wiggles on your seismogram. So that's a nice question. Snell's law is still okay. We haven't broken the Earth just yet. We probably will by some point today. Okay, so these are my phases. These are marked out now. And we see our inner core phase, which is the primary focus of today, is really going to be the first thing arriving at all these seismically relevant distances. We'll see that, sadly, our nice, well-behaved outer core phase, PKP-BC, is only there for a relatively restricted distance range, so we know that we're going to have trouble with reference phases at other distances. PKP-AB is lovely, and you can see deeper into the Earth using it as a reference, but we obviously have more deviation in the lower mantle, and though we have to be a bit more concerned about lower mantle structure. PK(IKP) at these distances is really, really soon after your inner core phase. Sometimes that's useful, sometimes you just get a big blur of energy. Okay, that's the terminology out of the way. There will be a quiz at the end before you're allowed any lunch whatsoever. So, I promised that the first thing we'd talk about was inner core anisotropy. This is how inner core anisotropy is going to work. We're going to have a fast direction and a slow direction. So if you watch this amazing PowerPoint animation again, you'll see that the blue line is meant to be going faster than the red line. It's not quite clear to me how well PowerPoint captures that. So fast and slow. We're talking here about P-wave anisotropy. So this wasn't really what Maureen talked about, because this is really the tool you want to use for the inner core, primarily because shear waves are just, well, we'll find out how hard they are later. But actually, for the inner core, you can see this P-wave anisotropy if you look at P waves which go through the same chunk of inner core at different angles. Okay? That's your P-wave anisotropy, going through the same material in a different direction. You're going to have a different velocity you experience. You're going to get a different travel time. So we have an angle. We want to define an angle. I promise I'm nearly done with the definitions. Zeta is our ray angle. Okay? You'll see some people use xi. You'll also see some people define it as 90 minus zeta. So if you're reading any of this stuff, you need to read kind of carefully. Zeta is going to be the angle between your wave in the inner core and Earth's rotation axis. So for all the purposes you guys should care about, we're going to say that inner core anisotropy is lined up with Earth's rotation axis. There was previously some discussion about whether inner core anisotropy maybe had a tilted axis. That's been settled now. I don't think there's anybody who would argue with me here. Okay, I'm safe. Fine. So we're just going to have this one angle that's going to tell us about the anisotropy we experience. And just so you have a feel for how we do this, we will normally have our reference phase and then look for where the bumps corresponding to maxima in our inner core phase arrive. You're seeing some predictions in the colored lines. You're seeing some really faint seismograms, so I now have much more sympathy for Jasper's vanishing red and blue. And if you see a bump before the blue line, the inner core is faster than you'd expect. If you see a bump after the blue line, the inner core is slower than you'd expect. And you have found some interesting structure somewhere in the Earth. So the first couple of papers to propose inner core anisotropy came out in 1986. There were some suggestions beforehand, but in 1986 there were a pair of lovely back-to-back GRL papers that said, we think that there is anisotropy in P waves in the inner core. Here are some body wave results, and here are some normal mode results. It seems to help us with both sorts of data. These figures are from slightly later. These two are from Ken Krieger. This one is from Vinnick and co-workers. They use two different reference phases. This is using the BC reference phase, and we see cos squared of the ray angle. We see that as you change ray angle, that's this axis, we see changing travel time anomaly, that's this axis. Things where you have a cos squared of the, in fact they have a xi here, close to 1, are faster than you would expect. So I've not just been making stuff up, that fast north-south path is what is seen here. If you plot this stuff as a function of epicentral distance, taken from the same paper, we see this isn't just a depth trend, okay? The fast stuff is at a range of depths. So we can't just say we've got some sort of radially varying structure. Instead, we have anisotropy in the inner core. That's backed up by this picture here, which is using that data set which looks deeper into the Earth, using the slightly more scatter-prone, longer reference phase. So we have anisotropy. There aren't that many data points here. I mean, it looks okay, but there aren't that many data points here. But that's okay, because you had Miyake's lecture, and then we played a little bit with normal modes, and we had two sorts of normal modes. We had the spheroidal normal modes, and we had the toroidal normal modes. So if I want to look at inner core structure using a mode I can see on the surface, which of these sorts of modes do I need to use? Fabulous. Okay, everybody is awake. This is amazing. So we're going to use these guys. These toroidal normal modes are basically, we said, SH modes. So although you can actually have toroidal motion in the inner core, you're going to completely decouple with the fluid outer core. So we're going to use these spheroidal modes, and we're going to have a hunt for anisotropy. Or rather, we're not really going to have a hunt for anisotropy, because what we're going to do is we're going to put up those two nice pictures from 1986, where people said, we have these interesting patterns. This is a pattern corresponding to the travel time anomaly for different sorts of inner core phases from that original paper. You see this striped pattern where you've got different sorts of anomalies for rays which are centered at the equator than the anomalies for rays which are centered at the North and South Pole. The details of this don't matter. Please don't think that it looks like a pair of evil eyes staring down on you. That's what happens if you stare at it too much. Here we have a terrible grayscale splitting function. We remember from Miyake's lecture that splitting functions told us about how one normal mode sees the planet. So a splitting function is your depth integrated at each point on the surface of a sphere. How does one particular mode see the planet? And this is for mode 13S2. So I'm now showing you 13S2 from a color paper. We have moved on out of the 1980s. And what you see in both the grayscale and in the color is broadly a stripy pattern. So in the color picture, we see blue at the top and bottom, and we see paler colors verging towards red in the center. This is the characteristic pattern of inner core anisotropy. This is how inner core anisotropy looks to a splitting function map. Okay? A stripy pattern. If you imagine a cylinder in the inner core, we can see that the symmetry have lines up with this stripy pattern. The details of that actually fall out quite nicely in the mathematics, and we're totally not going to push into any of that today. But if we look at splitting functions for a number of modes which are sensitive to inner core structure, we see this stripy pattern throughout. So these are splitting functions from a paper full of splitting functions. These are two modes which are sensitive to inner core structure. We have sensitivity kernels for the modes here and here. These are the splitting functions that paper measured. And these are the predictions for those splitting functions if you only include mantle and crust structure. So I think even from the back of the room, everybody should be fairly happy that the splitting functions we see here do not look like stuff generated by the mantle and the crust. Even though the sensitivity of some of these modes to the inner core looks tiny, and this should slightly freak some people out, the sensitivity looks really small, but what these modes really, really see is this really big pattern in the inner core of inner core anisotropy. So, I have no idea what you just said, Sana.
Sorry, is there an LSVP effect on that too?
So you definitely see a strong LSVP signal in both the mantle predictions. I would argue for this mode, this looks to me like some deep subducted material here. So when you make the predictions with S20 RTS, what you're really seeing with the predictions when you've only stuck in mantle structure is mantle structure. And certainly we do see some sort of blotchy pattern in these. They're not perfect blue, red, blue stripes. So definitely these modes see the mantle, which is good because the mantle is quite big, especially if the core is volumetrically insufficient. So these are the patterns we get.
Can I ask a question?
Wait for the mic, though.
So I guess if you look at the predict, the splitting function from crust and the mantle, and they're actually compared to your observed, there are actually some interesting correlations, right? Are they just created amplitude from the crust and mantle is, it's just much smaller than you observe. I mean, are they just a coincidence, or you think there are some possible connections?
So the first thing I would say is I didn't make these splitting functions, so while I would love to have all the credit for them, that should go to the author's paper. The second thing I would say is that what I was kind of trying to explain to Sana, that these predictions really are telling us about the mantle model we threw in there. They're not really telling us about the crust we threw in there, because these modes care about the whole planet, and the crust is really skinny. For these modes which have deep sensitivity, you do crustal corrections. You take into account crust. These are from crust 5.1, so you only need to think about big-scale crust structure. But yes, these predictions, and to some extent, the splitting functions, do give us some sign of what's going on here. But the sign that dominates the actual observations is the sign from the inner core. There's definitely a signature of the mantle that could be teased out of these. Although I would argue that if you want to look at mantle structure, you should probably look at mantle-sensitive modes, because this is a tricky signal to extract uniquely. Does that slightly answer your question?
I guess I'm not sure if the core structure would have anything to do the mantle and the crust structure. So, if you want to attribute much of your observation to the core, it's kind of interesting. There's a pretty nice correlation between the your observation.
Yes. So I think Barbara really wants to say something.
So if you were to show a splitting function for a mantle mode, right, you would see something that looks like on the right-hand side, right? You would see a C22S22 pattern mostly, not the C20 pattern.
I'm amazed at the first mode, 13S6. So
yeah.
The inner core sensitivity is, wow, it's almost 0.
I know, I said somebody in the room should be horrified.
I'm horrified. So the outer core sensitivity is huge.
Yes.
Any possibility there's some cylindrical tangent cylinder difference?
I have one picture later. So chances are slim to vanishing. Certainly, though, there have been some studies which have suggested observations of this structure, so I'll try and get back to that if I have time later. The outer core is pretty well mixed. The place that one could sustain lateral structure would be in the tangent cylinder of the inner core. So if people haven't heard of that, imagine a tube that contains the inner core with the radius of the inner core that's aligned north-south. So if one wanted to do such a thing, then that would be the way that one could put structure in the outer core. And there was a nice paper in 1992 that suggested that, because they looked at pictures like this and said that sensitivity in the inner core is tiny. Can't possibly be there. A follow-up paper the next year that produced an anisotropy model for the inner core actually showed that even that tiny bit of sensitivity with that model was enough to explain those results. But people still look at that. So I know Miyake, I don't see Miyake, but Miyake has looked at that. Barbara has looked at that. I will have a slide from, I think, Barbara's paper later on. So we'll try and get back to that if we have time. But yeah, people should be horrified, because this looks tiny, and yet it dominates what we see for this mode.
This is a really good point, which bothers me a lot.
Yeah.
That this particular mode has very little sensitivity and has a very large splitting. Some other modes that have more sensitivity to the inner core actually have less of an effect.
Yeah, I would completely agree with that. This is why this is one of our unsolved questions, right? Today I'm doing provocative unsolved core questions, and this is definitely one of them.
Just a quick comment. I'm right here. Can you go back to the previous slide? Just for the students, so the way you guys might want to think about these figures is you want to take the figures on the left, and then in your mind you want to subtract from those patterns the patterns that are on the right. What remains is the pattern that you can ascribe to the outer and the inner core in some proportion that I will not get into.
Okay, so definitely we have more than just an interesting mantle in our planet. I will throw in quickly here one caveat for the discerning seismologist, which is that many inner core modes seem to not like the self-coupling approximation very much. So nearly all of what you've heard in the past fortnight about normal modes assumes the self-coupling approximation. It says that our modes notice mantle structure, but it doesn't freak them out too much. They basically stay with similar eigenfunctions than they had before. So you'll see peaks broaden, you'll see maybe double peaks, you'll see splitting maps which aren't just one color. What actually turns out to be the case for some of the inner core sensitive modes is that they do actually freak out quite considerably when you put anisotropy in the inner core. And in desperation, they couple with other modes. And you can think of that as them going, my goodness, what have I just seen? And clinging to their neighbor so tightly that they interact with their neighbor, that their eigenfunctions actually are no longer perfect eigenfunctions, and that the eigenfunctions are mixed, and therefore the frequencies change and the quality factors change a bit. So depending on how you feel about normal mode seismology, you can either go for not quite being in the right basis set of eigenfunctions, or you can go for these terrified modes clinging to their neighbors and interacting with them somehow. Either way, it turns out that when you let these coupling interactions happen, you can actually see fairly substantial changes in behavior of some of these modes. So what I've done here is abuse models which were never built for this purpose. I've taken modes built using self-coupling, and I've let the modes interact if they want to. So what you see, I think I'd probably concentrate on this picture on the right here. We've got 4 different models of anisotropy. One is Barbara's model, one is Caroline's model. There are 2 other models there. They were not designed for this maltreatment, but I've let things couple anyway. And you see that compared to the data, which is the black line, we see different sorts of behaviors for this mode. This is 13S2, the one we saw before, which even in the self-coupling approximation is predicted to care about inner core anisotropy. But when you put in different models, this mode freaks out in different ways. So this is a cautionary note that we should be careful that stuff goes on with these inner core modes that you don't have to be quite so worried about in the rest of the planet. I'm not going to push on with that point much further, but if people want to talk to me afterwards about that, that would be tremendous. So fine. We've got anisotropy in the inner core. That's a bit weird. We're going to get into why later. But then things start to get messier. We're seeing here a figure made in, well, I don't know when the figure was made, but it was published in 1997. These are travel time residuals for PKP BC, PKP DF measurements. So these are those phases which are going to sample the top maybe 350, 360 kilometers of the inner core because of the reference phase we use. They're compared to a 1D Earth reference model. When you see dark colors, we're seeing positive residuals. When we're seeing light colors, we're seeing negative residuals. So we're seeing fast residuals with dark colors and slow residuals for light colors. These are just for equatorial paths. And there is a signature here of a degree 1 structure. The east seems to be different to the west. So we have an inner core. We said it's anisotropic. We're only showing the equatorial path, so this shouldn't be the effect of anisotropy. It turns out it actually kind of is. But what we're seeing here is a hemispherical pattern. This is plus 1 second, this is minus 1 second. If you take the polar paths, the things which are most strongly affected by anisotropy, the map looks like this. So we're seeing really big signatures, really fast paths in the western hemisphere of the inner core. Paths in the eastern hemisphere of the inner core, we're not seeing those big numbers. We're not seeing strong travel time anisotropy. We are seeing hemispherical anisotropic texture in the inner core. The east is different to the west. This is well after the end of the Cold War, but the east and west are different. Okay? Something else is going on here. It's not just the anisotropy. I show now a figure from a paper a little bit later. We have a bit more data. It's still not perfect for all sorts of reasons. What you're seeing here are fractional differential travel time residuals as a function of ray angle. You're seeing them for my preferred west and east hemispheres in red and in blue. I get to stand up here. I get to put my preferred hemisphere boundaries. We see this nice curve here with, varying degrees of fit, showing that the western hemisphere is really quite anisotropic, maybe more than 4% anisotropy. And the eastern hemisphere is not really showing much anisotropy at all. The figure on the right is the same thing happening, but I've used the AB reference phase. That's the thing that let us look deeper into the inner core, but with more scatter. So broadly, we're seeing a hemispherical pattern here. But not everything fits. This is not perfect. I don't have all of my red points on one line and all of my blue points on the other line. I see some rogue blue points which are invading and some rogue red points. I tried to make them behave, they would not. This story is troubling. It's even more troubling than when we saw those splitting function and sensitivity kernels. So the first thing that one might want to do is verify that these observations are at least telling us something that's vaguely true. So how can we do that? Well, we can go back to the normal modes. So this is now an observed self-coupled splitting function for 16S5. And we see the stripy pattern. Again, not perfect stripes. Again, there's other stuff going on. And if we would predict the self-coupled splitting function for this mode, we would get a picture that looked like this. I think this is with Barbara's inner core anisotropy model. I could be wrong. So, hooray. You know, we have a measurement and a prediction, and we see this stripy pattern in both. We don't see hemispheres. We don't see hemispheres here because one mode in the self-coupling approximation is mathematically unable to look for odd degree structure. So east versus west structure is hidden to one mode in the self-coupling approximation. That's just the way the maths falls out. I will say that if you predict what this mode should look like just for mantle and crust structure, you get something which definitely doesn't look exactly like what we see. Although you do see these traces where we know we have subduction zones, there are blue bits. Clearly the mantle model is seeing the mantle. So this is self-coupled. What you can do is you can look at cross-coupled splitting functions. You can let a mode terrified by this ridiculous inner core interact with its nearby mode. You can look at the pair of them, and if you do that, the mathematics says that that pair of modes can care about and notice and respond to odd degree structure. So that's what you see here now. This is a cross-coupled splitting function for two modes, one of which is only really caring about the inner core, and one of which cares about both the mantle and the core. And when you make this observation, you see this hemispherical pattern. We see a red dot mirrored by a blue dot. We see a blue dot mirrored by a red dot. We already see that my description of hemispherical is slightly tenuous because this is not a perfect mirror image. If you take, again, a model that was definitely not designed for this, hack it in half, you would predict something like this. So if you would put hemispherical inner core anisotropy into these models, you would get this, and this is what we see. Now, the model wasn't designed to be chopped up, so I would be kind of shocked if it had matched well. But with the normal mode data, we can see some sort of hint that this structure isn't just a body wave artifact. There is definitely some sort of big scale structure in the inner core anisotropy. If you would predict the cross-coupled splitting function just for the mantle, by the way, you'd get something that looked totally boring. This is yellow. It's not just the projector messing up this time. This is just yellow. That's because one of these modes is only sensitive to core structure. So it doesn't matter what you put in the mantle. These modes can't cling together because they're not both seeing it. OK. So this is where we've got to so far. We have observed cross-coupled splitting functions for a few modes now, which seem to show a hemispherical pattern. I'm going to skip this next slide and move on to the fact that things are never as easy as one would like. So we have two hemispheres. We have an east, we have a west. I showed you my perfect favorite magic line between the two. Nobody questioned me. I got completely away with it scot-free. You're all far too kind, or you're all just thinking about lunch. These are my favorite line and other people's lines of where the boundary might be between the east and the west. So they're not all in the same place. In fact, they range from about 10 degrees to more than 60 degrees in some cases. Which, that sounds okay, right? That's not that many degrees. You only get 360 degrees around a whole planet. If you want to divide it up into two hemispheres, you only get 180 degrees in each hemisphere. So if you're wiggling the boundary about by that much, that's a fair chunk of planet. The picture actually looks much worse, by the way, for the boundary in the Pacific. So is it that somebody is right and everybody else is wrong? Actually, there are a few people who pick lines very close together, so maybe they're all basically right, and there are a few outliers that are wrong. I think it's probably that the inner core structure is much more complicated than hemispheres. Hemispheres are a gross oversimplification of what we probably have. If you're in a spaceship, you've just come into the solar system, and you look at the Earth, kind of reasonable to say at the first order, I have a planet. It looks like a terrestrial sort of planet. Well done, you've just found inner core anisotropy. If you zoom in a little bit further, you're still seeing all the planets. Earth is kind of your blue marble. Then when you look at your blue marble, you could be forgiven for saying, I have a planet which is basically land on one side and ocean on the other side. Not a terrible approximation. I mean, the ratio's a bit off and the distribution's not perfect. But to first order, kind of a degree 1 planet. So to say that the inner core is perfectly hemispherical, I would probably argue is an oversimplification. Here is one of the ways you can peek into that oversimplification. So this is a data set with just under 2,500 travel time residuals. They're all going somewhere under Africa. The map isn't beautiful. We have equatorial data. We have less polar data. We are always struggling in the inner core with a lack of good data coverage. It's particularly bad for polar paths. That's why I alluded earlier to the nuclear tests. If you have a nuclear test in northern Russian territories and you pick it up close to the South Pole, you have a really beautiful polar path, and then you have a risk of starting another war. So we don't do that too often anymore. What you're seeing on the right of this figure is an inversion of this travel time data here using a super simplistic method which would probably make many seismologists from the 70s blush. I'm okay with this. The inner core's kind of hard. If you would partition your inner core here into 3 chunks, so if you imagine 1 stripe, 2 stripes, and 3 stripes, this is just plotted up across this east-west projection. The divisions between these, they're actually boxes. They're actual boxes. That's how retro this is. The divisions between these boxes are marked by these tick marks here and here. If you would invert the data for a 1-layered structure, you'd get slightly weaker anisotropy over here and slightly stronger anisotropy over here. Hemispheres. We've got different sorts of anisotropy on either side of my magic box model. If you invert the data and say, hey, we're going to do this amazing thing and maybe say that the Earth varies as a function of radius, which I know is groundbreaking, then what we actually see popping out here is an area with much weaker anisotropy overlying an area with stronger anisotropy. Okay? This layer is 250 kilometers thick. It's 250 kilometers thick so that about half the data turns in the top layer and half the data turns in the bottom layer. That is not an Earth-motivated choice. That's a parameterization choice that's probably going to make Ved cry, so I'm going to step away slightly. This is just one picture saying that, hey, maybe one magic dividing line between the 2 hemispheres is going to be a flawed idea, but it's still a good average idea. The normal modes see bulk structure. They see something which is basically hemispherical, but at the same time, that's probably an oversimplification, as, by the way, is dividing the Earth up into stripes. In the interest of time, I'm going to skip this next figure and move on to say this is a picture taken from a paper that's already 5 years old, where the author is saying that the inner core is complicated. In fact, what he prefers to say is a conglomerate of anisotropic domains. I think that might be too technical a phrase for the confusion we still have about the inner core, frankly. But why would one assume that everything is perfect? There is definitely a broadly hemispherical signature. You see it in the body waves, even though they're polluted by structure from the mantle. You see it in the normal modes, even though it's difficult to make those observations. So there's something broadly hemispherical, but I would argue that we're moving to the point now where pure hemispheres is really starting to be pushed away. On average, it's okay. But I think the details are something that we're going to want to start talking about, and I think this is really where these sorts of inner core seismology topics are going. And I would say that this is something that I didn't say in this way 2 years ago, and I think personally my thinking about this is getting stronger, that we really need to look at these details. And I don't know if Megan's here, but Megan already had a paper a couple of years back trying to look for detailed boundary in detailed places. So it's not just me saying this. So that's beautiful, that's seismology. This is our cartoon, this is my cartoon. And you can already see I've gone back to my nice east versus west. So cartoons are hard. We have a less anisotropic eastern hemisphere. We have a more anisotropic western hemisphere. I've not talked about it at all, but actually the very top, maybe 50, maybe 80, maybe 100 kilometers of the west are actually isotropic. So already there's another problem. I've merrily left a question mark in the middle of this picture. I'm not going to talk today about innermost inner core at all. My personal feeling is that that's not quite resolved yet, but different people may feel differently. So we've got a cartoon. And then we need to think back to our teenage selves and say, but why? Why do we even have anisotropy? Why does the inner core look like this? Why is it messing with us so much? It's this ball of iron that's slowly crystallizing in what should be a fairly well-mixed fluid. Why on earth does it look like this? So how do we make anisotropy? This is the interactive part of the talk. How do we make anisotropy?
Aligning crystals.
Aligning crystals. Somebody is still awake. Okay, so we can align crystals.
Two different phases and a texture.
Yeah, we can have different phases and make texture. Those are the primary ways that we could do this. Oh, we have more ways.
Single crystal.
Single crystal, we could have just one big crystal. Or two for the east and the west. And 3 for the middle.
4.
And a shell of 4. Okay, so we can have a small number of well-aligned crystals. There was actually a paper from 95 or 96 that slightly, I think, tongue-in-cheek at the end said, hey, maybe the inner core is just one big crystal. So grain size, we can add that to the list of stuff we don't really know. The anisotropy could be due to crystalline alignment. We can produce that alignment by thinking about thermal gradients or magnetic gradients. The structure may develop during crystallization, so we may, if that's true, be recording in the inner core what was going on in the deep earth at that time. So that would be tremendous. One of my friends uses the analogy of tree rings. Your tree ring tells you about what was happening as that bit of the tree was growing. So if we have texture that develops during crystallization, then that depth in the inner core tells us about what was happening as that bit of the inner core grew. So that would be tremendous. Or we might have a texture which develops after crystallization, so some sort of post-crystallization deformation, induced by whatever you want to induce it. Or we could have larger scale structures preferentially aligned in one direction. So here's one idea. I actually quite like this idea for reasons related to heat flow anomalies at the core mantle boundary. This idea by Yoshida follows the geodynamical arguments that somebody like John made on the middle of the week, where the heat flow is actually fastest on the inner core boundary outwards at the equator. So maybe your inner core grows just that bit faster at the equator. It's not hydrostatically stable, so in order to make gravity happy, to appease gravity, we'll get some sort of deformational flow that would take you from the grey ellipsoid back to the black circle. So that flow could line up crystals. That's one idea. I actually kind of like that because if you can vary the heat flow, then you can vary the degree of crystalline alignment.
This is out of weird curiosity. Why that paper is published in Journal of Physics Condensed Matter? Do you know?
I haven't got the faintest idea.
Okay.
I promise it is. I've not made up the citation. There are actually 2 papers that publish the same picture. There's one from 1996 and there's one from 1998. The reason I'm using the 1998 reference is because the picture came out in higher resolution. It's not a deeply technical answer. So I'm going to pause here, and what's going to happen is the next slide isn't going to load. It's loading, it's loading. So, of course, one thing that we would have to worry about for all of these is everything going to get destroyed anyway? So this is a movie from a paper that Sana wrote a couple of years back with Bruce Buffett. This is one representative case where if you play with the parameters, you can get different sorts of flow regimes, different sorts of behaviors in the inner core. This is one which I think, do you call it plume behavior? Is that fair? Maybe. So this particular case is for an inner core which has a CMB heat flux of 7 terawatts. It's got an age of about 1.1 billion years, and you can see that it is convecting. That should be okay, right? The mantle can convect. Why can't the inner core convect? We don't know if the inner core convects. We'll get back to that towards the end of today. But you can see that if you grew in some structure and then did this to it, it will be kind of hard to keep the structure the same. So we have to be careful about all of these interpretations, and these should all therefore be caveated by whatever you grow could get destroyed, but maybe not, we don't know. You reassured? Fabulous. Okay, so something else you could do to line stuff up, not the thermal fields, would be to look at magnetic forces. So there are a couple of different ways you could do that. This first one would actually help you line up crystals depending on whether your colloidal field was stronger than your toroidal field. You'd get different crystal alignments. I kind of wish John was here to comment on that. We could also say that maybe it's the Maxwell stresses in the inner core, again, some sort of magnetic argument, which could be causing these sorts of flows, these sorts of behaviors. With either thermal arguments or with the magnetic arguments, you can line up crystals when you grow them, or you can deform them afterwards. You have to worry about if they're going to get deformed by other stuff anyway. You can also do, wow, that's terrible. Okay, you can also do what somebody over there shouted out, and align up things with different properties. So this is a cartoon that I actually can't find on the internet, so I stole from Jean-Paul's slide, where there was the suggestion that you could line up frisbees of melt. Okay? If your frisbees of melt have their axis pointing north-south, then you can make anisotropy. We actually see attenuation anisotropy in the inner core, so your frisbees of melt will definitely attenuate waves going in different directions, different ways. This is a little bit tricky because we do seem to see anisotropy down to the center of the inner core, so you have to have some magic way of keeping your melt melty all the way to the center of the inner core. But it might just not be lining up crystals. We might be lining up bigger structures too. So we definitely have anisotropy. We definitely have spatial variation of anisotropy. The next step beyond that is to say we have a mechanism for anisotropy. We just don't know what it is because there are so many of them. There was one year where Shunkarato actually published 2 papers with 2 completely different mechanisms in the same year. So anisotropy is hard. Let's move on to something easier. Let's jump on to shear waves in the inner core, because that's so super easy that will be done in 5 minutes. So the inner core has a really low shear velocity. It has a shear velocity below 4 kilometers a second. Prem will tell you it's something around 3.56 kilometers per second. Because it's so slow, it actually turns out to be what seismologists would term a major arc phase. So instead of going the short way round, it actually takes off in the opposite direction and then bends backward on itself to go the long way around. PKJKP is a major arc phase. There have been a few observations of PKJKP. Nearly all of them are contested. Some of them are more contested than others. The first one is sadly in black and white, so I'm not even going to show it to you. This is the second attempt to see PKJKP. So what we're seeing here is a seismogram stack on the top, and we're seeing those seismograms inspected as a function of frequency on the brightly colored panels. The bottom brightly colored panel is a zoomed-in portion of the top brightly colored panel. PKJKP is predicted to arrive in this time window. This is PKKP, so that's a P wave through the mantle, travels through the outer core, bounces, travels back through the outer core, spouts back up through the mantle, all P waves. It interferes horribly with all sorts of stuff. It can tell you cool stuff about the properties at the core mantle boundary, and in particular the underside of the core mantle boundary, for people who are thinking about that sort of thing in their research group. So we see in the frequency domain a big bright color around the travel time of PKKP. So these fairly high frequencies, that's about 0.8 hertz, that's high frequency for global seismology. We see PKKP clearly, and according to the authors, we also clearly in the time domain see little p, PKJKP. So that would be this thing or this big smeary thing here. PKJKP should be here. These are very hard observations to make. They're also very hard pictures to look at. Okay? PKJKP is a difficult phase to see unequivocally. This is looking at seismograms. I think this is from some of the geoscope stations in France. There are 8 stations here. Not many stations. It's from the atomic energy. I'm mistaken. So this is only 8 stations.
What's the difference between the top and bottom panel?
So the middle panel, the middle colored panel is, we've got frequency and travel time. So we're inspecting the seismograms and looking at their frequency content. The bottom panel is just the same thing zoomed in. So we see our frequency axis here only goes from 0.1 to 0.5, so we've essentially zoomed in and really ramped up our color scale in order to try and convince people that there is something here.
But the arrival time of these phases would be consistent with 3.5 to 4 kilometers per second?
It would be consistent. It would be, and towards the 3.5 kilometers per second end of that. The previous paper, the one that I'm not showing, actually had a really low shear velocity of about 2.95, and nobody has ever seen anything at that sort of speed again. So this is consistent with Prem values. Whether it's there or not is harder to discern, but this would be Prem-like. So a brief interlude, because I'm about to plot a picture with a different variable. Slowness tells us about when a phase arrives at different stations sitting next to each other. If you have a slowness close to 0 and you're at one station, the next station along is going to see that phase arriving really quickly because it's coming nearly straight up. If you have a much bigger slowness, then the next station along, it's going to take a while for the NG to get there because it's going basically sideways. There's a distance between you and the next station. So slowness you can think of as how quickly a wave sweeps across a small, dense array of seismometers. This is yet another slide hijacked from VED. This is from 2 years ago. You can actually look at slowness across a global array of seismometers too. And one thing that's useful is that waves which are coming from different depths in the Earth will be coming up at different angles and will have different characteristic slownesses. So instead of just having to inspect frequency content, what one could try and do is look at the angle that waves are coming up at, so their slowness, across an array of stations, be that a tight array or a broad array, and see if that can help us get rid of the other phases arriving at similar times, but at angles we just don't care about. So we're going to use slowness. This is now one observation. We're seeing travel time as a function of slowness from some sort of array measurement. This is actually from, it's not really a dense array, this is just stacking many stations together. This paper suggests that there's an observation of PKJKP there, and that maybe in this circle there is an observation of little p PKJKP and SKJKP. So that's a shear wave for its first transit through the mantle. The little p says the seismic energy goes up, bounces off the surface before behaving as a regular PKJKP. So that's nice. We've got a nice picture. We've got some stuff circled. Should you be convinced? What if it's meant to look like that even without PKJKP? So one test you can do is to calculate what the synthetic, in this case, vespergram would look like, so slowness, as a function of time for a model with a solid inner core and then a fluid inner core. Because if you turn the inner core to fluid, or you just kill its shear velocity to be super low, then you shouldn't expect to see PKJKP. So in that case, things that are different between the solid inner core and the fluid inner core are things which care about the inner core. So if you do this test, you do what VED recommended for the splitting function, to do a mental subtraction. There is something red, arguably, in each of the PKJKP observations. But the thing in this circle here, those green blobs, the green blob is there for the solid inner core and seems to vanish for the fluid inner core. So maybe this is an observation of little p PKJKP and or SKJKP. Other people have looked using similar techniques. This is Amin Cow and Barbara, and they again looked for PKJKP. In this case, they were using the Grafenberg array. And again, they see something where when you subtract out other phases, looks like it could be PKJKP. Other papers have been published, so we have observations of potential surface reflections, we have observations of potential PKJKPs themselves. This, I'm not going to dwell on the blurry, smeary mess that the projector has turned this into. This is a suggestion that somebody has seen PKJKP split, as in shear wave splitting, which is what Maureen has been telling us about already. So this is shear wave splitting in the inner core. This observation would say I see two PKJKPs. It's not just that I really need to clean my glasses. It's that we have two distinct polarizations in the inner core. They get converted back to P waves as they leave. So we trap that travel time difference caused by the anisotropy. So this is the only, as far as I'm aware, the only suggestion that somebody has with body waves seen shear wave anisotropy in the inner core. To make this work, you actually have to make Q infinite in the inner core. So parts of the inner core, you have to take away all attenuation. So to make their models fit, it was a little bit tricky, but they do have this suggestion of this split phase. And I will say, just for people at the back who really love blurry pictures, this is published, it's actually published last year, not this year. This is an attempt to see PKJKP and then convince everybody that they've seen PKJKP by performing absolutely every single test under the sun. So this is work by Lauren Vacek, and she's done normal mode modeling, she's done spec-fem modeling, she's subtracted this from that, from this, from that. There seem to be places where the only thing you can ascribe signals to are PKJKPs. But this is hard. Why is it this hard? Are we just not good at this? There's a really nice paper from Peter Scheer and co-workers in 2011, and he does what is so difficult in all of science, and he publishes a null result. Okay? It's really hard to sneak those past the editors and the reviewers who say you haven't found anything. But in this case, the interesting story is, why is it hard to find PKJKP? So stacking global seismograms for the whole planet, for all the earthquakes, Scheer and co-workers have a hunt for PKJKP. So we're seeing global stacks of data. They're lined up on PP. That's a phase that travels through the mantle, bounces to the surface, travels through the mantle again. They're normalized on that phase. PKJKP should be arriving somewhere in this broad time window. If you believe PREM, that's PREM plus or minus 10%. If you make a vespergram of data from the whole planet, now we're seeing this vespergram rotated. I'm sorry about that. We've got slowness over here and travel time over here. That broad PKJKP window should give us a bump in this box. It does not. If you stack every seismogram on the planet, you can't see PKJKP. These are the differences between some synthetics where you should be able to see PKJKP, where it should be present, and some synthetics where it should not. Can anybody see differences? I'll tell you, there is a dashed line, and you can see a dashed line and dotted line. That's going to be really hard to convince people with. That's why we probably can't routinely see PKJKP. It has very, very, very little impact, even at these frequencies where it should work. So if you look at the abstract for this paper, it says routine observation of PKJKP is unlikely, and reported observations, if real, it's kind of a bold statement, must have resulted from exceptional focusing effects or inner core attenuation much less than current models. So basically, we're getting off lucky here. If we've seen some stuff, then we've had a good day. So do we know anything about shear wave velocity in the inner core? Because I said it was hard to match PREM with mineral physics. It actually turns out that as well as freaking out about other stuff, inner core sensitive modes do freak out if you change shear wave velocity too much. So what we're seeing now is some synthetic spectra. So you'll see a bump wherever there's a normal mode shaking. So frequency down here, and some sort of normalized amplitude here. And the normal mode peaks really jump about if you make the inner core fluid. Okay, so we can, with normal modes, say that we need something which is PREM-like. It might not be perfect PREM, but it should be fairly close to PREM, unless you want to dance some of these modes about.
Jessica, I think it would be fair to say that we know that the inner core is solid from normal mode observations. There's a paper by Jaworski and Gilbert.
Yes, that's completely true. So I would never claim that it was fluid, and in fact, Barbara's right, and I actually had to take out the slide from that seminal Jaworski paper, where the inner core was proven to be solid. It's at 1971 by comparing normal mode observations. This is by no means the first time that this was done. This is just a picture that's pretty. When you have the slide from Adam's paper, you actually just have to have a table and some misfit results. Normal modes will not permit a fluid inner core. Normal modes will not permit an inner core which is totally different from PREM. So even though PKJKP is hard to see, it's still possible with normal modes to say that we have some faith that we know what we're doing. We have some faith that we should be close to PREM, because that's what the normal modes asked for when PREM was created. That's what put that data in there in the first place. Many questions?
You showed a number of the body wave studies, but you weren't very specific on how well they agreed with in terms of shear velocity in the inner core. I think you said the first one was way off.
Yeah, so the
others,
the very first one was way off. The others, I would say, all broadly agree with each other and with PREM. I don't know if Barbara is an author on one of these, and I'm not, so if she would like to... There you go.
My detection, quote unquote, was 9 seconds early.
Okay, so that is a bit of a travel time anomaly. In fact, I would say that's about the size of the splitting between the two PKJKPs that the Wookiee paper saw.
Okay, so from the normal mode data and the body wave data, what's the range of allowable velocities? Like, are we talking 1% variation, 10% variation?
figure somewhere in supplementary slides, but I don't remember the numbers. You certainly can't have 4 kilometers a second. Everything is broken by 4 kilometers a second. Depending on how you balance your VP and your density, there are obviously inherent trade-offs playing this game. And many of those calculations are done assuming that the center frequencies aren't perturbed by mode coupling, which in fact some of them are. So you have to be a little bit careful when you play that game. But certainly 4 kilometers a second is no go. Could you go up from 3.56 to like 3.7? Could you go lower if you need a slower arrival, that 9 seconds? I think those are all viable. I would be cautious to give you more numbers off the top of my head.
If I asked you to put a bound on Q in the inner core, what would you say?
I would say, is it lunchtime yet? So Q in the inner core is hard. Okay, Q everywhere is hard. Q in the inner core has 2 components, as does Q in general. We have the inherent analyticity of minerals. We also have scattering. If you want to talk about scattering, you should talk to Wembo, who's my graduate student. He's been looking at scattering in the inner core using pk coda. That's the noisy stuff that comes after pk, which is the stuff that bounces on the inner core boundary. There are a number of different techniques one can use to look at Q. That's just one of them. If you look at Q with normal modes, obviously you're basically trying to remove that scattering information because you're only seeing intrinsic attenuation. Q in the inner core is really low. So you're talking about, it's in Prem, it's 84.6. So that very small Q, it's a very high attenuation. I would honestly not like to say much further at this point. Q is difficult. It may not inherently be Prem-like. All of our observations are challenging. Q also trades off, by the way, if you're trying to fit normal modes. So add Q into your mix of VP and VS, and then remember that inner core mode coupling can change the relative amplitudes of modes because essentially you're in the wrong basis set, so you can pump energy from one normal mode into another normal mode.
I think there is evidence that Q increases with depth in the inner core. I think most people would agree.
Yeah, I think that's fair.
Whether it's due to scattering or other.
Yeah, and so if you would look at body wave studies that have used, for example, spectral behavior or relative amplitudes of PKP DF compared to an outer core reference phase, people have made relatively detailed, in those case, QP models, and they do see that attenuation is less severe as you get deeper, which of course makes physical sense. You've got something which is further away from its melting point. If you had any little bits of melt, you've probably got rid of those. If you're growing crystals slowly, you might have had a chance to anneal those crystals. That feels okay. Some of the models actually have peaks and then troughs, and they oscillate a bit as you look at Q as a function of depth. Those observations seem to be mostly in regional studies, I would say. They're not. There are some nice regional studies out of HiNet. With HiNet, you have so much data that you can interrogate this quite carefully. They're basically QP studies, but obviously Q kappa, so bulk attenuation, is so much bigger than shear attenuation that it's shear attenuation changes that are probably dominating that behavior. Okay, so now I'm going to skate on to the next topic. This is a stolen cartoon from a CIDER project. This is the idea that John talked about briefly. This is inner core translation. We'll see how far we get through inner core translation. There are a beautiful pair of papers in 2010 from 2 different French groups who both argued, with different reasoning, that it might be possible and plausible and true that the inner core is slowly sliding sideways in the center of the Earth. So this is a degree 1 translation. That's what the attempt of this animation is trying to show you. The inner core is translating sideways, I'm not quite sure what the skateboard would represent in that case, through the outer core. Okay, so how and why did they propose this? The first paper was actually trying to explain a slow layer at the bottom of the outer core. So remember when we looked at those 3 red, green, and blue models of VP in the outer core, and the inner core in fact, and we saw that the places where they matched least well were actually close to the boundaries. It turns out that other models relative to Prem and in fact other models subsequent to these relative to each other, say that the bottom of the outer core is a bit slower than one might expect. So this study was trying to explain that behavior amongst other behaviors. We're seeing some tank experiments here. I've never done a tank experiment. This looks tricky. What the setup is that there is a sponge at the bottom of a tank. The tank is full of saline. Dense, higher salinity material is injected at one side, and material with a similar salinity is injected at the other side. The system is allowed to evolve. Depending on what sort of salinity contrast you have here, you can, in some cases, set up a dense, stable layer. It's not all just convected away as this system progresses. That's the experimental setup. So now everybody's completely beflummoxed. Why on earth am I talking about dense saline next to less dense saline? Why on earth am I talking about saline at all? How is this even slightly relevant to the outer core and the inner core? If the inner core is crystallizing on one side and melting on the other side, the side which is melting will release more dense material. If your light elements prefer to stay in the outer core and you start melting the therefore more dense inner core, you release dense material. Even if you only release dense material at one side, which remember is what this study did, it released dense material on this side, and you can kind of see that in this early time snapshot, and regular material on the other side, your stably stratified layer can actually give you something that's dense, in this case across the whole box. So this study was saying that maybe we can explain, amongst other observables, this dense layer at the bottom of the outer core with melting on one side of the inner core and crystallization on the other side of the inner core, as well as explaining a bunch of other hemispherical properties about the inner core. So this is one way to do it. To make this work, you have to be releasing stuff which is sufficiently dense. It doesn't work otherwise. There's a density threshold, both in the experiments and also there are some, they ran some numbers in the paper as well. So that's one of the papers. The other paper actually came at it from an angle which is much easier for me as a seismologist to see. They looked at the top of the inner core at these travel time anomalies. Remember I said that we had different travel times in the east and the west. I also in passing mentioned that the top is isotropic everywhere. You don't have to worry about anisotropy. So these are now isotropic travel time anomalies in the east and the west. They collected some new data, very comparable to what other people have seen. We have blue points in the western hemisphere. We have red points in the eastern hemisphere. So clearly the top of the east and the top of the west are different. Maybe one way to do that is to slide the inner core slowly sideways, crystallizing on one side, melting on the other side, so that on one side you've got material which is brand new, and on the other side you've got material which has been hanging around in the inner core for ages. It's traveled the whole way through. Okay? So that could explain both some of the velocity data and some of the attenuation data. So we have these two papers, which clearly the geodynamicists love, because it makes lots of fun with their models. They both had pretty cartoons. One was in Nature, one was in Science in the same year. So is this okay? Can we do this? Because other studies have seen what appear to be relatively sharp boundaries between the Eastern Hemisphere and the Western Hemisphere. So there was a lovely CIDER project. That's a CIDER stamp of approval from the 2012 program. And I think the topic was topic deep time or something like that. So the way this project worked was that they tried to see if you could make inner core translation be compatible with what seemed to be seismic observations of relatively sharp boundaries between the East and the West. So this is a figure that they made to show how material gets translated. So it grows at point G. Do you guys know how long it took me to realize why their points are labeled M and G on the original paper? It's because G is the growing point and M is the melting point. It grows at point G, and then stuff slowly moves across as the inner core translates. It's growing on this side. It's melting at point M. So you have an age progression of material. They then generated a synthetic data set. So they ran, for randomly oriented and located data points, they ran waves through the model with younger and older material. and looked at what sort of signals those seismic data would see. So their predictions from this synthetic data set are the pink points. The black points with error bars are some binned averages for an earlier observation by Vacek. And you can see that you can kind of, I'll take that away for a sec, you can see that you can kind of look at that and say, you're basically within all the error bars. So maybe it's not terrible that these bin seismic data see something which is roughly equivalent to the translation data. It's not perfect. The seismic data kind of looks flat and flat. This definitely has a curve. But the seismic data suffer from uneven sampling. So okay, maybe as a seismologist I should be happy with this idea. It turns out that when you think about the mineral physics one would need to create these sorts of amplitudes, there is only one possible model of iron which they found that could fit that data. So the purple line, you can get away with fitting. But for any of the other models of what iron could be doing at relevant temperatures and pressures, you can't actually reproduce a sharp translation with this dramatic difference between east and west. I personally don't love the idea of inner core translation because I find it very difficult to see how one would make anisotropy that was quite different in the two hemispheres. So my personal bias using Occam's razor is probably that if you need two mechanisms, it would be nice if you could just have one. That's not science, though, really. What is science is the work that's been done by a number of people, primarily led and published by Marine Leblay and a number of people in France, where they looked at where different sorts of behavioral regimes were possible in the inner core. So they were looking in geodynamical, non-dimensional number parameter space and saying, what sorts of things could our inner core do given different physical parameters? So this is a pretty complicated picture here, and I'm not going to delve into the details of it too much. Suffice it to say that essentially we're thinking about the age of an inner core on one axis. We're thinking about viscosity, in fact log of viscosity on the other axis. And you'll remember I told you that inner core viscosity was incredibly poorly constrained. So you will see on this picture the viscosity here goes from 10 to the 10 to about 10 to the 26. So that's a big parameter space range they're exploring. In different places, different convection or translation or behavioral regimes are possible. We see in particular that whether you convect or not really depends on whether you're on this side of the picture with plume convection or translation, which is just a particular sort of convection, by the way. And over here, we see behaviors which are much more stratified. So depending on your age of your inner core and your viscosity, and there are other parameters one could tweak and roll into non-dimensional numbers, you will get different behaviors. And for translation to happen, in this particular model, your inner core should be younger than 300 million years old. That's a super young inner core. You have to have an inner core which actually is younger than some of the plate reconstructions would claim they can get back to make this work. You can change other parameters. Other behaviors are possible. You can pick your favorite viscosity. Certainly some viscosities are required. For example, we see translation is up here. So you need your inner core to actually be relatively rigid in order to push it rigidly sideways. Otherwise, your surface will just deform and bring you back to equilibrium. So I would say that this is probably a bigger problem for the philosophy of inner core translation than maybe my disliking it because you can't make anisotropy using it. One can also think compositionally about what would happen. This is a picture where composition is also taken into account. We now have compositional variation as well as viscosity variation. I'm not going to push into the details, but what I would like to highlight here is the sentences in the conclusion, which say, a mechanism able to explain the strong anisotropy revealed by the seismic data would have to satisfy two requirements: that the induced strain is large enough and the flow has the correct geometry. So they're trying to match up with what's seismically seen. And by the way, they're trying to match up with what's seismically seen before we add in the complications of hemispheres. Based on our regime diagram, they write, this seems to require either stable stratification and a viscosity large enough to reach the weakly stratified heterogeneous growth region which could give flow with adequate geometry. And they refer to the Yoshida paper. And they refer to the earlier Yoshida paper, not the later Yoshida paper. However, the timescale of texture development would be similar to the age of the inner core. One of the problems with the Yoshida paper is it takes a while to build the texture, and we think we see quite a lot of it. Or low viscosity and either stable or unstable stratification to allow the Lorentz force to have a strong effect. So the other way you could make the anisotropy is maybe by exploiting the Lorentz force if you can hit a viscosity sweet spot and get your behavior quite right. So I would say here that there are clearly a lot of parameters, even in the geodynamical sense, that we really don't understand about the inner core. I was going to talk about the outer core briefly, and then I was going to talk about heat flow at the core mantle boundary briefly, but instead I think what I'd like to do is say it's going to be lunch soon and stop 5 minutes early so we can have a discussion about some of this stuff. Or we could just go for lunch.
I guess for the inner, for inner core, and if it's so rigid, can actually go through this translation. What do you think about the geotherm? They actually follow the adibet. I guess typically when we think about adibet, it's a kind of convective state, and so I guess it's a question. I guess I actually kind of have a comment on the degree 1 structure, and so you showed the seismic, I guess the travel time differences between the two hemispheres, east and west. So if you think, let's say if it's due to temperature, what maybe could be composition, could be anything, right? Let's say it's due to temperature. What actually would be the temperature anomalies between the two hemispheres that actually can give you that kind of travel time differences?
I think it would be very difficult to justify temperature heterogeneity between the east and the west. I mean, we normally think about the outer core being isothermal, right? I think you're not going to do this with temperature. One could make that calculation. The parameters are a bit uncertain.
If it's due to the convection, then you'll have to east west hemisphere.
So the amplitudes of the temperature anomalies on that convection picture were of the order of 1 Kelvin, I think, between the maximum and minimum in the inner core, on those convection of the inner core simulations. I don't know about for the Leblay pictures. I think the geotherm question is a great one to punt to next week's workshop about the geotherm, because I wouldn't like to speculate on how that would behave. And I'm sure Jackie would love us to talk about that next week.
I was curious about convection in the inner core. What is the driving force for that?
You get convection when you have inherent instability. So it's not quite stable. A little perturbation will set you off.
Temperature driven, though.
Temperature or density. I'm going to push this question to Sana, because I showed her movie. And she looks so thrilled that I've just done that. Do we have a second microphone? Thank you.
I mean, you can get convection from compositional variations or from temperature variations, but it's mostly just the core not cooling fast enough since at this peak the outer core.
So these calculations would be done for compositional instability. These calculations are really thinking about that thermal instability.
But that seems backwards to me, that the outer core is getting progressively more enriched in the light elements over time, which also means that the stuff on the outermost part of the inner core should be getting progressively lighter, which is stable stratification, owing to composition.
Yes.
Right? Well,
so oxygen is the one that would strongly partition outwards. Then you can ask your favorite mineral physicist about the partition coefficients of other stuff. Oxygen wants to go up. I've seen numbers which suggest that silicon and sulfur are more equivocal. Yes, and some of the models actually for this stratification, for the convection, will have it switching on and switching off at different times.
It could be something people argue with, but Prem tells us that can't be right. Prem tells us there's more light elements in the outer core than the inner core.
It does.
Which means the light element prefers to partition into the outer core.
Yes. And definitely the density deficit is mostly compensated by the outer core. The outer core is responsible for most of that density deficit. I would again caution against believing Prem right at that inner core boundary, because Prem is parameterized as smooth polynomials and can't completely capture small changes in gradient close to a boundary. But Prem is mostly true.
I meant to say seismology, not Prem.
That's okay.
But the question that you raise is actually one of how dynamic the inner core is with respect to remixing later alloying components is into the interior. And that's a very interesting question I think you've raised. Because you're correct, there should be a small gradient in composition across as the outer... Yes, with lighter stuff growing up, unless it is a dynamic situation where you're perpetually remixing the core.
A sense of the magnitude of isotropic and anisotropic velocity variations in the inner core, because I feel like we saw plots with differential times all the way from 0.02 seconds to 1 second.
Yes, so the anisotropy signature is stronger than any isotropic difference. The anisotropy numbers people reach will vary from study to study, but we're talking of the order of 3 or 4% anisotropy, P-wave anisotropy. That's normally taken to be the difference between the fastest direction, which is north-south, and equatorial. It actually turns out, and this probably might be slightly more interesting for some of the mineral physicists, that equatorial, or 90 degrees from fast, isn't the slowest direction. In many models, the slow direction is about 60 degrees from fast, which of course will bring to mind exactly what's making that slow direction. So you will see variations in exactly how people talk about that. And that's common to many models, but not ubiquitous. And of course, we do see places where the anisotropy is much weaker than that, if it's present at all. The other thing I would say is that when you average over those curves of anisotropy, you would actually get Voigt velocities which are often really quite similar to within maybe 0.1, 0.2, 0.3%. So it looks like the Voigt velocities as you average over the entire sphere, in effect, may be more similar. At the top of the outer core, so in that isotropic layer, you're seeing maybe half a second, maybe up to a second travel time difference, when your core transit is probably of the order of, I would guess, 80 seconds over the top of my head. So, I mean, they're not huge anomalies. They're not, for instance, as big as the VS anomalies we would see in the lower mantle. And I think Barbara wanted to say something.
I just want to remind you what Rudy said very quickly at the end of his talk yesterday, that in order to get 3% anisotropy, you would need to have a single crystal, essentially, in the inner core. I think that's an important issue.
And I think
right
that's
now,
troubling.
with the current knowledge on mineral physics.
That's if the anisotropy arises from crystal-preferred orientation. So you can get anisotropy from texture or lining partial mill.
Yeah, but I think it might be quite concerning if one needed to align the entire inner core as one crystal and yet have some regional variation. That seems troublesome, just on a logical sense.
Well, that tells us that it's not LPO.
Yeah.
That tells us that either it's not LPO, or the seismology is not yet fully understood, or the mineral physics isn't yet fully understood. Okay, so I actually have one announcement, which is somebody has found a black cardigan. I have no announcements left.
Thanks.